We've been using exhaustive algorithms, guess and check algorithms. When we got integers, we saw that's nice because there's only going to be a finite number of solutions, but we won't be able to find, say, square roots or cube roots of numbers where that isn't a perfect square or perfect cube. We've generalized that to look at something that does a different kind of guess and check, where we take incremental steps, still enumerating all the possibilities within the resolution of that step, trying to find the solution. And we saw that that either means we take very small steps and we take a long time, or if we take larger steps, we might miss the solution. And I suggested we want to find a more effective way of doing that. So here's an example of that and a wonderful tool that we're going to see a lot as we go through the course. It's called bisection search. Let's think about square root. One of the things we know about the square root of a number is that it lies between 1 and that number, if that number is bigger than or equal to 1. We'll do fractions in a second. So square root of 25 lies somewhere we know between 1 and 25. Here's the basic idea. Rather than trying everything starting at 1 and taking small steps, suppose we pick a number in the middle between 1 and say 25, 12 and a half. If we're lucky, that's going to be close enough. Well, it's probably not close enough in this case. We know where it is, but it's a nice start. But we can take that idea and generalize it. If it's not close enough, then we can ask, well, was the guess too big or too small? And in particular, if that guess g squared is bigger than x, we know it's too big. So what can we say? Well, we know that the answer has to lie below g. And that's really cool because it says all of this stuff here, throw it away. I don't have to look there. I know that the answer has to be somewhere between 1 and g. Do the same thing. Pick something halfway between. That's my new guess. Try it again. If it's close enough, I'm done. If it's not, ask the same question. And for example, in this case, if g squared is less than x, then we know it's too small. So we can throw that stuff away and only focus on this portion. And again, pick something in the middle and keep trying. You can already see why this is going to be really nice, because on each step, I'm throwing away half of the things that I don't have to look at anymore. And that's going to let me hopefully very quickly zero in on finding the right solution. That's a wonderful idea. It's called bisection search, and we're going to use it. So what did we say? At each stage, I'm losing half the values. Really cool. Let's see what happens if we wanted to actually make code for it. So this is a little bit of a busy slide, but we'll walk through it. This is an example of computing square root using that example of bisection search. I'm going to start off just giving it the thing I'm going to look for. X will be 25. That's the thing I'm going to use as the root. Again, I'm going to pick something that I'm going to use to tell how close I am. And I'm also going to keep track of how often do I actually run through the loop, just to compare it to what we saw earlier. I need to set a low value and a high value, the range in which I'm going to look. Initially, that is 1 to the number itself. And then I'm going to make an initial guess, which is halfway in between. Just high plus low divided by 2. And then I run through one of those nice little loops. What do? I say, if the difference between the answer squared and x is bigger than or equal to epsilon, I'm not close enough. And in that case, I'm going to print out some information, increase the number of guesses by 1, and then do what I just did, which is if answer is too small, that is, its answer squared is less than x, then I can change the low part of the range to move up to answer. And if answer is too big, I can change the high part of the range down to answer. As I did before, I start out here. If answer was too big, I change the high range to bring it down into there. If answer is too small, I bring the low range down into there. And I keep sorting it down until I get into something that's reasonable. This algorithm just captured that idea I just described. So let's try it out. We'll do it with 25. Here's a bisection search on square root. And if I run this code, wow, it actually got there very quickly. It did it in 13 guesses. I'll remind you, in the previous case, we took 30,000 guesses to get there. I don't want to print all that out on my screen. And notice how quickly it zeroes in. It starts off with low 0 and high 25. And then it says low 0 and high 12.5. And then low 0 and high 6.5. You can see if you look at the printout how quickly it narrows in on the range. That's really cool. Okay? Do the same thing with cube root. I can do exactly the same idea. This is almost exactly the same code. The only difference is I'm using guess cubed rather than guess squared. And I'm going to keep track of otherwise exactly the same information. And let's compare that. If I go over and pull up my cube root example, we'll start with 27. Again, I'll remind you that in this case I was doing 30,000 checks to deal with this. Now I run it, and in 14 guesses, it gives me a really good answer. And if I pick something that's not a perfect cube, like 54, and I do the same thing, in this case it took 15 guesses to get me a really good answer. This is a powerful tool. That idea of bisection search, throwing away half the possible values at every stage, lets me very quickly zero in. As before, I can ask, well, can I do everything? This is only going to work for numbers bigger than 1. What about fractions? Well, I know with fractions between 0 and 1, now the difference is that the root doesn't lie between the number and x itself, it lies between 0 and that number. But that's an easy way to change, and we could actually think about making that change. But just to remind you of how powerful this is, notice what happens. If I start off with the number n, on the first guess, I reduce the set of things in half. On the second guess, I reduce it by another half, so it's now n over 4. After g guesses, I've got a range that's only n over 2 to the g. And what this says is that in an amount of time that is going to grow as the log of n, I'm going to get to an answer. That's really nice because it says I don't take linear time, I actually take less than linear time to get there. We'll come back to that idea later on in the course, but this is a great example of a logarithmic time algorithm finding an answer very quickly. I jumped ahead a little bit because I already started talking about what happens if I want to look for cubes only greater than 1. I could modify it to look at negative cubes, and I could modify it to look at things where the answer is less than 1. And so, for example, if x is less than 1, I just changed the search space. So now, rather than going from 1 up to x, it goes from 0 to x. Rather than going from 0 to x, I want to go from x up to 1. I'm not going to do it. I'm going to leave it for something you to try out, but it's really easy to make that change. And again, notice what I've done. Start with the basic set of code, check to see what it runs on, and then decide if I wanted to use the same code, how could small changes have it run on other kinds of solutions? What can I take away from this? Bisection search really radically reduces computation time. I went from 30,000 times through a loop to 10 or 15 times through a loop. That's really nice. And this should work on any problem with what we would call an ordering property. That is, the value of the function being solved varies monotonically. That is, it increases as the input value increases. G squared has that property. As I change g, it grows. G squared grows as g grows. G cubed, same kind of idea. So bisection search will work on any problem that has that kind of property. We're going to see more examples of that as we go through the course.